Welcome back to my channel. In this video, we will discuss a very important topic, that is a stability factor. Every time you can observe the question from this topic, which is very important. The topic is stability factor. Every time they're asking a question from this, and you might see the question like find the stability factor for a particular biasing technique. Or otherwise, they might give a numerical question. But any one thing is for sure. And sometimes they will ask you the both combination of these two. Like they will ask you to find the stability factor for particular biasing technique and then a numerical problem. So we'll see this one. First of all, if you see this stability factor means like it will show the sensitivity of this collector current with respect to IC naught. And at the same time, this collector current with respect to beta. The collector current with respect to VPE. It means at what extent, at how much the collector current is goes on changes with respect to this isomorph. That will depends then stability factor. So out of these three, all these three are getting affected with the temperature only. Out of these three, we are trying to focus only on the IC naught. Whenever he was saying about an stability factor means, then that stability factor will indicate that change in IC with respect to change in IC naught. By default, we must consider this one. This is very important. Keep it in mind. Of course, we can also see the stability factor that is change in IC with respect to beta also. That is dou IC by dou beta, and at the same time dou IC by dou VP also we can see. But out of these three, IC naught will get affected more with the temperature. Due to that, we are considering only this dou IC by IC naught. So simply in the examination, he will tell that to find the stability factor. So that in that case, we must consider this formula. Now, if you see the main three biasing techniques, we can see here. Actually, here there are three biasing techniques are there. We already know it, right? What are these three biasing techniques? Um, if you see these three biasing techniques, the first one is fixed bias, and then second one is collector to base bias, and then third one is voltage divider bias, which is very important. Like actually, these three are the biasing techniques which are most commonly used, and this is a part of our syllabus. And in the question, they might ask you anything. Like they will ask you the direct question, like find the stability factor for a fixed bias, or otherwise collector to base bias, or otherwise voltage to divider bias. Now we'll see one after the other. Now, if you see here, the first one we'll go through it. Like the first one is we'll try to find a stability factor for fixed bias. We'll see this one first of all. For this one, we must know the circuit diagram of this fixed bias. How this fixed bias will looks like. First of all, always we have to prefer the common emitter only. And then here one resistor will be there, that is RC. And then here one resistor will be there, that is R1 we can say. Or RB also, your wish. Here I'm saying it as an RB. Here it is VCC. This is the circuit diagram we can see. Right? This is a fixed bias circuit. This is a fixed bias circuit. This figure is a fixed bias. So by using this one, we have to find the stability factor. That is dou IC by dou IC by dou IC naught. We have to find it. So how to find it? Already we know that the collector current of IC is equals to beta times of IB plus 1 plus beta times of IC naught, right? So somehow we have to find this base current in this circuit. Then we have to substitute that value in this expression. Then we'll get an IC. And that IC we have to do the differentiation with respect to IC naught. Simple. Then we'll get a stability factor, right? So for that case, we'll try to find an IB now. So how to do that? Now let us try to applying a KVL here. Here, if you see here, the voltage is VPE, and then what is the current here? The current is IB. So let me try to apply an KVL at this outer loop. KVL at outer loop. Let me apply KVL at outer loop. Then what it will become here? Minus VCC. Nana. Here entering, I'm saying it minus VCC here. In the first case, minus VCC. What is the voltage in here? IB into RB. That is plus IB into RB. And then here voltage, that is VPE plus VPE is equals to 0. Then as straight I'm directly writing this IB. What I'll get, this IB is equals to VCC minus VPE divided by RB. I'll get it. Very simple. In this way, I'll get it. So now I got an IB. Now let me substitute this IB value in IC. Now if I'm writing here, substitute this IB in IC expression. Then what it will become? Let me write it again otherwise. IC is equals to beta times of IB plus 1 plus beta times of IC naught, right? So here let me try to substitute it. Here IC is equals to beta times of IB. IB value is VCC minus VBE by RB plus 1 plus beta times of IC naught, like this. Now we'll try to do the differentiation on both the sides. With respect to IC naught, we have to do it, right? Now we'll do it. Differentiate with respect to IC naught. Now what it will become? That is dou IC by dou IC naught, right? So what is the derivative of this term? This is a constant. Derivative of constant is 0, right? In the here, whatever this one, 1 plus beta is a constant I'm taking out. So dou IC naught by dou IC naught, which is 1, right? So this stability factor, that is S, which is dou IC by dou IC naught, is equals to 1 plus beta here. So what I can conclude, this stability factor I got is 1 plus beta, which is very, very important. You must remember it directly. He might ask you the expression, or he might ask you the numerical problem also. If you're asking about the numerical problem, then we can use this formula directly. Or if you're asking the proof means, then we must do all these kind of things. Very simple. This is the stability factor for fixed bias. So the thing is that if you observe here, in the case of a fixed bias, it is this stability factor is very, very high, right? It is very high. It means a poor stability, we can say. But because whenever there is a variation in the IC naught, the collector current is goes on changes. Actually, this collector current should not be changed with respect to the temperature. If that changes, our Q point will get changes. So that is why we are trying to find the stability factor. This stability factor should be as small as possible. That is the point. Now, we'll try to find the second one. We'll go with the second one, that is stability factor for collector to base bands. The second one, stability factor for collector to base bands. For collector to base bands. Again, we must know the circuit diagram for collector to base bias. How to draw the collector to base bias circuit? Again, CE, here RC. From the collector to base, this is the collector. From to base, one resistor will put it. That resistor I'm calling it as an RP, right? Here, this is the ground. This is an BCC, like this. This is the circuit diagram for collector to base bias. Here we can give a figure name. This figure name is collector to base bias, right? Now we'll try to find this one. Again, we have to do the same thing. Dou IC by dou IC naught, we have to find it. And for that case, we know the standard expression, that is IC will be equals to beta times of IB plus 1 plus beta times of IC naught. So again, we have to find the IB in this expression. How to find this IB in this expression? Again, we have to apply the KVL on here. What is the current here actually? Here the current is actually here at this terminal, the current is IC. At this terminal, the current is IP. So what is the entering current, Nana? Leaving current is IP and then IC. So the entering current should be combination of these two. That is IC plus IP, which is approximately equals to IC, I'm saying, which is approximately equals to IC. But because this base current is very, very small. Now we'll try to apply KVL in this outer loop, Nana. What is the voltage here? Plus minus, it is VBE, right? Now we'll try to apply the KVL at the outer loop. Now we'll see here. Let me do here itself. KVL at outer loop. Let me say. What will become again? Minus VCC. Minus VCC. What is the voltage here? IC into RC. No, no, here IC into RC plus IC into RC. Then what is the voltage here? IB into RB plus IB into RB. Then what is the voltage here? Plus VB plus VBE is equals to 0. Like this, we got it. Now, can I write it directly? The base current of IB. Let me write it directly. The base current of IB is equals to VCC minus VBE minus IC RC by RB. This is the base current, right? Now, let me substitute this base current in the standard expression. What I will get it? Let me write it again, otherwise here. Wait a minute. Yeah. Now, here let me write it. What we did, we find the base current. Now substitute IB in IC expression. So IC is equals to beta times of IB, right? Beta times of IB. In place of IB, I'm writing this expression. In place of IB, I'm writing this expression. That is VCC minus VBE. That is VCC minus VBE minus IC RC divided by RP plus 1 plus beta times of IC naught, right? Very simple. Now we have to do the differentiation. Now we have to do the differentiation. Actually, before doing this differentiation, here the collector current is there, here also the collector current is there. Let me try to take it common. Let me put this collector current on the one side, then it will become easy. Let me do some modification, that is IC here. Let me send this beta in inner side. Here beta times of VCC minus beta times of VPE minus beta times of IC RC plus here 1 plus beta times of RP I'm taking here. I'm taking whole denominator as RP here. Whole denominator as RP. Now, what it will become this? Let me take this away this side, then RB into IC. Let me take this term also on this side, then it will become plus beta times of IC RC. And then remaining parameters are BC, beta into VCC minus beta into VBE plus 1 plus beta times of RB IC naught. Right? Very simple. Hope everyone understood this one. Very simple point. Now in these two, let me take a common ICS common. Then it will become RB plus beta times of RC, right? And the rest of the things are same. That is beta into VCC minus beta into VPE plus 1 plus beta times of RB IC naught. Now let me try to find the IC collector current. Then what it will become here, beta into VCC minus beta into VPE divided by RB plus beta times of RC naught. I'm writing it separately, right? Plus 1 plus beta times of RB IC naught divided by RB plus beta times of RC. Like this, we'll get it. Now we'll do the differentiation. What it will become if I do the differentiation here? Let me do differentiation on both the sides with respect to IC naught. Then dou IC by dou IC naught. Then what is this one? It is a constant. It will become 0. Now this entire term I will take a common now. This entire term I will take a common with this is a constant. The dou IC by dou IC naught, what it will become? It will be 1. So I left with 1 plus beta times of RB divided by RB plus beta times of RC into 1. Now this is a stability factor. Now stability factor, how much I got it? Stability factor, that is dou IC by dou IC naught, will be equals to 1 plus beta times of RB by RB plus beta times of RC. This is the expression I got it, right? Now if you see here, now if you compare the previous one at this point, this stability factor will be less than 1 plus beta here. So we can say that it can provide and a better thermal stability compared to the fixed bias. But because here the stability factor is less than 1 plus beta. There it is 1 plus beta, which is very large. But because beta value is basically 50, 100, 200, 300 like that, which is very, very large. Here it is even less than 1 plus beta. So it can provide, let me write the conclusion here. This stability factor S is less than 1 plus beta. Actually, this is the formula now. You must remember it directly. This is the formula, which is very, very important. Now, this stability factor is less than 1 plus beta. And then we can say that it can provide a better thermal stability compared to the fixed bias. It can provide a better thermal stability compared to fixed bias. Well, because in the previous case, the stability factor is 1 plus beta. Here it is less than 1 plus beta. But I already told you the stability factor should be as small as possible, right? Now we'll see. This is the case for the collector to base bias. The next part is we'll try to find the stability factor for voltage divider bias. Voltage divider bias. That is stability factor for voltage divider bias. Voltage divider bias. So again, here we have to know the circuit diagram for voltage divider biasing circuit. So how to draw this one? Again, we will prepare the common input. Here R we will use it here extra. Integration RB and then RC. Now here let me choose indicating as an R1. Here it is an R2. This is connected to the ground. Then this is an VCC. Now what does this figure mean? It is voltage divider bias. Voltage divider bias circuit. Now let me try to draw its equivalent diagram. By using Thevenin's theorem, we have to find this equivalence. This equivalence value will be equal to how much number? This is C into R2 divided by R1 plus R2 equal to 2. And then R Thevenin's value will be equal to R1 is in parallel with R2, which is R1 into R2 divided by R1 plus R2. And this way will be taken. So if we draw this equivalent diagram, then what are we getting here? This equivalent diagram will give here. This will be RC. This is in a BCC. At this base side will get R Thevenin's. And then here we will connect B Thevenin's. That is B Thevenin's. And here one impact resistance of RB. This is connected to the ground. So now we have to do the same expression. Like again, we have to find the IB and we have to substitute the IB value in IC. I'm doing the same thing again. Here, let me try to apply here the KVL. That is plus minus the voltage will be V here. Let me try to apply the KVL in this point. By applying this KVL, here let me try, we can say this VThevenin's. It will be VThevenin's, and then what will get here? What is the voltage across this point? Across this point, what is the voltage? At this point, the current is IP here. At this point, the current is IP. At this terminal, the current is IG. Yeah. Here we'll try to apply the KVL. Then what it will become? Here it is V Thevenin's. This is the voltage, and the here voltage will be IB into R Thevenin's plus IB into R Thevenin's, and then here the voltage will be VBE, and then VBE. Here the voltage will be IE into RE. IE into RE. It will be equals to 0, right? By using this one, let me try to find this VThevenin's. VThevenin's will become, actually here this VThevenin's will be minus entering, right? Entering, and the rest of the things will become positive only. Then VThevenin's will become IB into RThevenin's plus VBE plus IE into RE, I will get it, right? Up to this was like very clear. After this one, here what we have to do, here we have to find the enter current. Actually, we know this enter current. This enter current of IE will be equals to, it is a enter current is a combination of IC and IB, right? We already know this one. At the same time, we know the standard expression, that is IC is equals to beta times of IB plus 1 plus beta times of IC naught. This is the standard expression, right? Now, let me try to substitute this IC value in this one and this expression. Then this IC, this IE will become, I'm substituting that IC value over here. It will become IB into beta times of IB plus 1 plus beta times of IC naught plus IB aggregated, right? Now this is the expression aggregated. Now in this expression, if you observe here clearly, again in these two things, I can take IB as common. If I take IB as common, the inner part will be here 1, here it will be beta. So 1 plus beta times of IB aggregated, right? And then rest of the parameters 1 plus beta times of IC naught. Very simple enough. In these two things, in this one and in this one, I'm taking IB as common. If I take IB as common, the remaining parameter will be 1 here, and then here it is beta. So that is why inner parameter will be 1 plus beta. And then this is the thing, I'm writing the same thing. So in this case, if I take again 1 plus beta as common, I can take 1 plus beta as common. Then the inner parameter will be IB plus IC naught. This is the one I can get it. So this is an emitter current I got it. Now let me try to find this VThevenin here. Now let me try to substitute this IG value in VThevenin's expression. Now we'll do this one. Now what we do, substitute this IE expression in VThevenin's, let me say. Substitute IE in VThevenin's. Substitute IE in VThevenin's expression. Or we can also give some equation names. Otherwise, leave it. This VThevenin will be equal to IB into RThevenin's. VThevenin's will be equals to IB into RThevenin's. This one, Anna. This is the expression. VThevenin is equals to IB into RThevenin's plus VBE. I got plus VBE plus IE into RE, right? IE into RE. This one. IE into RE. In place of, let me write it again here, otherwise it gets confused. IA into RE. Now from this here, let me substitute this IE value over here. That is what we are doing here. Within will be equals to IP R Thevenin's plus VBE plus IE in place of IE, I can write 1 plus beta times of IB plus IC naught RE, right? This is what we can write it here. Again, what you do, just try to send these two parameters instead of this one. Then it will become Vthernans will be equals to IB into Rthernans plus VB. I'm sending this 1 plus beta and RE instead of this one. Then it will become 1 plus beta times of RE into IB, right? At the same time, 1 plus beta times of RE into IC naught. Like this, I'll get it. Now, if you see here, in these two parameters, again, I can take IB as common. Then this expression will become, if I take IB as common, it will become R Thevenin's plus 1 plus beta times of RE, right? And the rest of the parameters are plus VBE plus 1 plus beta times of RE IC not I'll get it, right? This is the one I'll get it. Now, if you see here in this expression again, let me write IB on this side. IB of R Thevenin's plus 1 plus beta times of RE is equals to, I'm sending this one onto the other side. Then it will become V Thevenin's minus VBE minus of 1 plus beta times of RE into IC not LBT. Then finally, I will try to find the expression of this IB. This IB will become V Thevenin's minus VBE divided by R Thevenin's plus 1 plus beta times of RE, right? Then minus 1 plus beta times of RE IC naught divided by, I'm writing it individually, separately. This R Thevenin's plus 1 plus beta times of RP. I'll get it. Now I'll try to substitute this IP expression in IC, right? Substitute this IP in IC expression. What is the IC expression? The standard one that IC is equals to beta times of IB plus 1 plus beta times of IC naught. This is the standard expression, right? In this case, I will substitute this IC is equals to beta times of IB. What is the IB? This is the expression that is V Thevenin's minus VBE divided by R Thevenin's plus 1 plus beta times of RE minus 1 plus beta times of RE IC naught divided by R Thevenin's plus 1 plus beta times of RE. Now plus 1 plus beta times of IC naught, right? This is the expression I got it. Now let us try to do some modifications over here. Now let me try to send the beta value inside, then we'll try to do the differentiation. Okay, now here let me send this beta value inside, that is beta into V Thevenin's minus BCE divided by R Thevenin's plus 1 plus beta times of RE, I will get it, right? Here if I send this beta inside, then I will get 1 plus beta times of RE IC naught divided by R Thevenin's plus 1 plus beta times of RE, I'll get it. Here 1 plus beta times of IC naught. Now we'll try to do differentiation with respect to IC naught on both the sides. Then what I'll get it here. Now differentiate with respect to IC naught. That is dou IC by dou IC naught. If you see, then it will become 0 here because this is a constant. Here I can take as a these all terms are constant, and dou IC naught by dou IC naught it will become 1. So 1 plus beta times of RE divided by R Thevenin's plus 1 plus beta times of RE. Again here again I can take 1 plus beta as common, then dou IC by IC naught will become 1. So if you compare these two, I can take 1 plus beta again a common, right? This dou IC by dou IC naught, if I take 1 plus beta as a common here, Then inner part will be 1 here. 1 minus, it will become beta times of Re divided by R Thevenin's plus 1 plus beta times of Re I will get it, right? This is the expression I will get it. Now let me do further modifications here. This expression will become 1 plus beta uh, R Thevenin's plus 1 plus beta times of Re minus beta times of Re divided by R Thevenin's plus 1 plus beta times of Rp, right? If I send instead of this Re, one last modification here, this R Thevenin's plus Re, I'm sending this Re inside, then it will become beta times of Re minus beta times of Re divided by R Thevenin's plus 1 plus beta times of Re. Like this expression, I'll get it, these two terms will get cancelled. So finally, we will get this stability factor is 1 plus beta times of R Thevenin's plus Re divided by R Thevenin's plus 1 plus beta times of Re. This is the expression I got it. So if you see here, in this case, overall the stability factor, I can conclude it. The stability factor is this one. This is the stability factor for voltage divided by a circuit. This is the stability factor. If you see this stability factor, it is even. It is here also. It is less than 1 plus beta only. So by giving this, by using this value of this Re, we'll get this stability factor even less than 1 plus beta, and it can provide better thermal stability compared to both the biasing techniques. That is compared to fixed bias and corrected to phase bias circuits. Here, let me try to write it. Mm, it can provide better it can provide better thermal stability compared to fixed base and voltage to divert bias. Compared to fixed bias or sorry, not a voltage divider bias, like that is connected to base bias. And this is the stability factors for all the three biasing techniques. Just go through it. I will share this file in the description. And in the next video, we'll see the 2 to 3 problems on this biasing techniques. Thank you.